Welcome back to ECE 220. Today we're talking about root mean square, RMS. It's something you probably see stamped in a lot of different places, and today, hopefully after today, you'll feel more comfortable or confident in what that means or what that represents. As far as announcements, your homework, your next to last homework is due today. And you'll have one more homework assignment on Chapter 9 material. And as you know, that all of that's not on exam number 4. There will be one problem on phasor analysis on exam number 4, which is in a couple of days. Thursday is our exam number 4, and after that we will not have a class on that Friday, and we will also not have a class the last day of classes, which is a week from tomorrow. We're going to look at root mean square, really try to motivate it in terms of why are we interested in it, and that's this problem of the average power absorbed by a resistor given some periodic waveform. Is there a more convenient way to express the voltage level in terms of as a strict periodic waveform, or can we now find a value that's maybe as informative when we're asking about the average power? So let's look at that now in terms of this question. Suppose I now have a resistor. Maybe it's not a resistor. Maybe it's something that I'm modeling as a resistor. Think light bulb, and it's now being powered out of a socket. This is now a sinusoidal waveform expressed as a cosine. That's the reference sinusoid that we use in this class, and we're not giving it a phase, but it does have a frequency of 60 Hertz, which in terms of radian frequency, that's 377 radians per second. It has an amplitude of 170, and we want to know what is the average power absorbed by that resistor. How might we find that? Or what's a way to find the average power? This is maybe somewhat of a review for the final. How do I find average power? Or what is power? And here, this particular voltage is impressed directly across that resistor. There's nothing else between the voltage source and that resistor. How would you go about answering or approaching that problem? How are you going to find the average power absorbed by that resistor? What's the instantaneous power? So now I'm making a distinction between average power and instantaneous power. What's the instantaneous power of that element, that resistor? How do you think of that? And I actually wasn't intending to indicate that current going in that mesh. I was going to try to have you think of that, but if you're thinking in terms of instantaneous power, how might you parameterize that? What is little p of t? I squared R, it's V times I, where V is the voltage dropped across that circuit element and I is the current through it. If we now said, oh, that's I squared R, that's another way of saying instantaneous power. I squared R. And what is I? That's Ohm's law. I we can find as a function of time in terms of our sinusoidal input. If I now call this V of t, then I of t is just V of t over R. And if we now plug that into our instantaneous power formula, I now have V of t over R, that quantity squared, times R. That's I squared R. If I cancel some R's, I have an R upstairs and an R squared downstairs. I end up with an R downstairs and a V squared upstairs. Now I've rewritten the instantaneous power in terms of that sinusoidal voltage that's impressed across that resistor. What's the average power? How do we find average from an instantaneous? We know V is going something like this. That's V of t. How do we find the average of that? Integrate over a period or a length, and in fact the period is the more effective way to do this. You want to go at least over a period. You could go over multiple periods, but then you divide by that time interval. And in this case we're actually squaring the voltage before we find its average. So here we're going to say, oh, the average power is now 1 over t, where now I'm saying that t is from peak to peak. That's our period. We now want to integrate, and we can integrate starting at any point on that curve as long as we go one period beyond that. And we can say, okay, let's just say that's P of t dt. Or that's now 1 over t times this integral from t0 to t0 plus t of v squared. Well, maybe let me pull out the r. Let me pull out the r. I have 1 over r. Let me keep the 1 over t here. And that's now one way of writing this average power associated with that resistor, or the average power absorbed by that resistor. That looks a little messy. Would it be easier, or maybe I shouldn't say easy, maybe I should just say nicer. Wouldn't it be nicer if we could find an effective voltage that produced the same average power? Could we now find one value, one number, instead of having to worry about squaring, then integrating to find the average? Wouldn't it be easier to just kind of lump that into one value and say, oh, I know the voltage, let me say, or this effective value, let me now square that and divide by R, where I've now replaced what's in square brackets with this more effective voltage or nicer quantity. In other words, can we now compare that and say, can we instead think of this as some effective voltage squared divided by R, which, if we now compare this formula to that formula where the 1 over R has been factored out, do you see that this is now what I'm now calling the effective voltage squared, what's in square brackets? Or down here, I'm now saying, okay, I'm saying that the effective voltage is in fact what was in the square brackets, 1 over t, t0 to t0 plus t, v squared of t dt. Or, if we want to know in fact what that value is, v effective, we just take the positive square root of what's on the right hand side. Or this is now the square root of 1 over t, integral from t0 to t0 plus t, v squared of t dt. And in fact, this is now this effective voltage we've now actually tried to motivate or define what is called the RMS voltage. This is now the root, the square root of the mean of the square of v of t. And I like to, when somebody says, oh, find the RMS value, I sort of like to work from the right side and go back, and it makes it a little bit cleaner. We first square the periodic waveform, then we find its mean, and then we take the square root. That's the RMS. So this is now what is referred to as the RMS value of some waveform. In our case, that's this voltage v of t. And we'll then just call that v sub RMS. That's now a number that consolidates or compacts this information that was contained in this question. What's the average power of that resistor when we plug in that voltage or put that voltage across that resistor? On average is really what we're interested in. And can we now boil that down into, that was some crazy time-varying waveform, can we now just rewrite that and say, if I just had a value of voltage that was constant with this VRMS, it would now provide the same numerical value for the P average. So let's now compute the RMS value associated with a sine wave. And in particular, let's just stick with our reference. Let's look at this cosine, and we'll treat it in general. We now have some amplitude, V sub m, on that cosine. We have a frequency, omega, in radians per second, and we even have a phase shift, theta. And hopefully we're comfortable with that phase shift. We know that that's just sort of determining the value of this V of t at time t equals 0. Let's now compute for that sinusoid, for this cosine, its RMS value. And we want then the root of the mean of the square. So the last thing that we will do is we'll take the square root. We will first square that waveform. So that's now V sub m squared cosine squared omega t plus theta dt. We want to now find its mean, so we integrate over a period and divide by that length of time. And if we can now find this number or expression, we'll now have a way. You give me a sinusoid, I'll be able to tell you what the RMS value is of that sinusoid. Does it depend on omega? Does it depend on theta? Does it depend on V sub m? Does it depend on the period? That's what we'll try to determine. Let's now rewrite that. Let's just pull the v sub m out. That's constant. That doesn't depend on time. We can pull that outside or in front of the integral. We now have 1 over t, or let me just say we now have v sub m squared 1 over t integral of t sub 0 plus t cosine squared omega t plus theta dt. Now we have to integrate cosine squared. That's kind of a mess, but we can rewrite that. We can rewrite that using our trig memory, or we could actually prove or verify that formula or that trig identity by using Euler. And the one that we're going to use now is to rewrite that cosine squared as 1/2 plus 1/2 cosine 2 of the argument, omega t plus theta. And before we get too much further into this messy looking expression, let's just look at what happens to the cosine piece. If we now look at what will happen to the cosine piece, we're integrating over one period of cosine of 2 omega t plus theta. So we're now looking at what's the picture that we could sort of draw. I'm not sure I want to be drawing this, but let's say we now have, oh boy, that's supposed to be a cosine of the same frequency throughout. It's not supposed to distort. So that's supposed to be peaking consistently. And what are we integrating over? Now realize that we've doubled the frequency. We have 2x in our argument, 2 times omega t plus theta. So we're now going to see 2 maximums across one period. And maybe it'd be better if I just say, let me just make this period go from here to there. Here's now the one period of the waveform. Let me get the right location. It's now this. I've now gone through 2 humps and 2 valleys. So I'm integrating over that one period, and hopefully you can see what I'm trying to suggest, although my drawing is not going to be representing that. The positive area should equal the negative area if I'd drawn this accurately. Are we comfortable with that? Which means that if we now start integrating this over 2 cycles in this one period interval, the positive area equals the negative area, and consequently that leads to a 0 result, which now allows this piece to not have to be concerned with. We've now essentially said that goes away when we do this integral. And that allows us now to appreciate rewriting cosine squared as 1/2 plus 1/2 cosine of 2x. That means then that Vrms for this sinusoid is Can I go ahead and take the v sub m squared outside the radical and just call it v sub m? I now have v sub m, and I have the square root of 1 over t integral from t0 to t0 plus capital T of 1/2 dt. Since that circled note is supposed to have convinced us that that cosine of 2x piece doesn't influence or impact the result. And now we simply do the integration. And hopefully you see that the T naughts cancel and the capital T's cancel, and we're just left with, under the radical, 1/2. Or the RMS value of a sinusoid is now this famous formula, the amplitude, or V max, over the square root of 2. Where this was just the amplitude of the cosine, and we could have rederived this for the sine, you would see that it would give you the same formula. And VRMS, that doesn't depend on the frequency of that sinusoid, it doesn't depend on the phase, so it's pretty clean in terms of a value. This is independent of omega, or frequency, and the phase theta of the sinusoid. Does that now help us with the problem that we started the class with, which was what's the average power absorbed by that resistor? Now we can say, oh, we've replaced what was in that messy square bracket with a value, an RMS value. We now have this picture, and instead of having this time-varying waveform, we've now replaced it by this constant value, V sub RMS, where this is now what it was before. And now we can use our tools from the beginning of the class and say, oh, VRMS is V sub m over the square root of 2, where V sub m in that earlier example was 170, and that's actually the amplitude of the voltage that's coming out of the wall in the United States. It's now a maximum of 170, so we're going between plus 170 and minus 170, but everything you see is labeled as 120. So that's actually the result of that division of 170 by the square root of 2. That's where this 120 volts comes from. That now allows us to say, oh, the average power of that resistor, we just square that and divide by R, and that 144 resistance was conveniently selected. If you now look at what we have here, we now have 12 squared times 10 squared upstairs. We have 12 squared downstairs. the average power of that resistor of 144 ohms was in fact 100 watts. So this is the resistance, effective resistance, of a 100 watt light bulb. Did we talk about what we look like as far as our average power as a human? We're basically 100 watt bulbs sitting here, just brightly shining. That's why when you get 100 of us in a room, it takes some AC to cool the place down. We have light bulbs sitting in every chair, and they are representative of a 100 watt bulb. So if you go through and calculate, well, how does that work? Well, typically you say you consume maybe 2,000 calories a day. An average person, if you do the conversion, that ends up being, oh, we are constantly just like a 100 watt bulb. So when I see a 100 watt bulb, I think, oh, that's what we are in terms of the power demands that we represent. Let's look at RMS values for other waveforms. Are they all going to be what we just calculated? And on your homework, the next one, I think, you have one of these problems. Suppose this is now x of t. X of t, let's say, is 1, and then it goes to 0, and then it goes to 1 again. It's now this periodic waveform, and that's what we are computing RMS values for, our periodic waveforms. We now have a magnitude of 1 that is on for 1 unit of time, and then it's off for 1 unit of time, and it just periodically repeats. What's the period of that waveform? What's the time interval over which you have unique values before you start seeing that pattern repeating? It's now 2 units of time. Our period is now from first peak back to that first peak occurring again. So let's now find the RMS value for that little x of t. We now take the square root of the mean, so we're dividing by the length of time. We're integrating from 0 to 2 over 1 period of x squared. But now we have to remember that x has a functional shape. It's only 1 over half of that time interval. So when we do the integration on the non-zero part of x, we want to just integrate when it's non-zero, from 0 to 1. And I'm picking these to be really challenging integration problems. We now have to integrate a constant, so that now we have the square root of 1 over 2 t from 0 to 1, or we now have the square root of 1/2, or we have the magnitude of the non-zero portion divided by the square root of 2. And that looks very familiar. And so now you might be saying or thinking, is an RMS value always going to have this form, v sub m over the square root of 2. What's your guess? Pardon? Hopefully. Unfortunately, no. So you can't just immediately write down your homework answer necessarily, but maybe we'll help you with that if we can get through that. Let's now look at some others. The RMS value, in fact, depends on the functional form of this periodic waveform. The RMS value depends on the periodic waveform. If this was, let's say, example 1, let's say now example 2 is y of t. Suppose now we have 1, but now at 1 it transitions to minus 1. And it just continues to do this flipping of value between plus 1 and minus 1. What's the RMS value for y? If we simply plug in the formula, we square it, we take the mean of that squared value, and then we take the square root of that, the square ms, so the RMS, we would now look for the period, which again is 2. We integrate from, let's say, 0 to 2 of y squared of t dt. But now what happens to y when we square it? The negatives flip up. We've now converted everything to just a value of 1. We now have the square root of 1 over 2, 0 to 2 of 1 dt. So there, the RMS value is just 1 of that periodic waveform that was going back and forth between plus 1 and minus 1. No square root of 2 in that particular for that waveform. Let's look at another one. Suppose we now look at this waveform. Let's call it W. Has an amplitude of 1. This is now a sine of t. And you may hear this particular waveform called or referred to something. Have you ever heard of a half-wave rectified sine wave? We're just basically putting this sine wave through some diodes, and we're clipping off, or we're eliminating the negative portion of the sine wave. So we're just keeping half of the wave. This could be referred to as a half-wave rectified sine wave. What is W RMS? And this one might be close to what you're doing on your homework. Pardon? Which is due in a week from today. I think. So now what's the period? Two pi. We now integrate from 0 to 2 pi of w squared dt, where now we have to realize that w squared, if we start averaging this, we have to realize that w squared is only non-zero over half of that interval. We still divide by the full period, 1 over 2 pi, but now we just integrate from 0 to pi where that wt is non-zero. And now we can recall another trig relationship. We can say, oh, sine squared of t is 1/2 minus 1/2 cosine of 2t. And if you wanted to convince yourself of those identities, now that you have Euler just in your hip pocket, you're just best friends with Euler, you know what's cosine in terms of complex exponentials. Now, if you simply use this and square it, you should be able to derive those right-hand sides and convince yourself, oh, in fact, using that, we can find that cosine squared is 1/2 plus 1/2 cosine of 2t, or sine squared is 1/2 minus 1/2 cosine of 2t. That's now going to allow us to rewrite this expression for WRMS, or let's just not get quite there. Let's just look at the integral, which was sine squared from 0 to pi, 1/2 1/2 minus cosine 2t dt, where this is the sine squared. What's that second term going to do? What's the frequency of this now that we've doubled it? Omega is 2, and omega is also 2 pi over cap t, or 2 pi f, where f is 1 over t. If we solve that for t, we now see that the argument is just one period of a cosine waveform, and we're integrating over that one period, where the period of that cosine of 2t is from 0 to pi. So that now we are now seeing that we have the same areas above and below this particular integral vanishes or goes to 0. So that now we have the integral from 0 to pi of 1/2 dt that's going to be sitting inside our radical, or we can now say that the RMS value of this half-wave rectified sine wave is now the square root of 1 over the period. The period was 2 pi, pi over t. The pi's cancel. We have the square root of 1/4, or this is now 1/2. The RMS value now of this half-wave rectified sine wave turns out to be 1/2. What if somebody said, well, I want to see what happens when we have a full wave rectified case? Now we do keep track of, we flip the negative half of the sine wave into the positive side of its values. This is now over 1 period. This is still sine of t. We have a magnitude of 1, and let's call this z of t. This is now a full wave rectified case. And what is the RMS value of that z of t? Take the square root. And maybe I should have labeled this. The period, pi. We now have this integral from 0 to pi of little z squared dt and we've already seen what that integral of sine squared yields. This is now the square root of 1 over pi. That was now pi over 2. Or this is now the pi's cancel, and we have 1/2, or the square root of 1/2, or 1 over the square root of 2. Which shouldn't surprise us, because this should present the same effective power as the sine wave itself, because we're squaring that before we, or in the process of finding the average power. So with all of this information, what is the average power absorbed by this resistor in this circuit, same circuit? There's x of t. Let's just say r is equal to 1, and now I need to show you what x of t is. It's a periodic waveform that's triangular. And it now, let's say, is going every 2 units of time, and let's just make the slope convenient, or now we have that slope as t. How do we find the RMS value? That you should be very comfortable with at this point. Take the square root of the mean of the square of that waveform. In finding the mean, we have to find the period. Period of that waveform is 2. The functional form is t, or now we have the square root of 1/2 t cubed from 0 to 2. And can't forget our 1/3 as a result of the integration. Yes? Pardon?
I was just confused with the other example. You had z of t, but we had z squared instead of t squared. So I'm thinking, wouldn't this be x squared?
So this is now x squared of t. Is that what the question is? But now x squared, or x, is just t. So now I was immediately replacing that with what its functional form was and then squaring it. So that's where the x squared now was. I just didn't explicitly put it in there. But now we can see that this is the square root or two over the square root of 3. A little bit bigger than 1. That's the RMS value associated with a voltage that has this triangular wave shape. And the nice part about having the RMS value is now we can use that immediately in our average power expression. We now have that this is 2 over the square root of 3, and the R value was 1. We're squaring that, so now we have 1.33 watts for the average power of that resistor when that resistor is excited or driven by this triangular wave shape. So the computation of the average power wasn't that challenging once we found the RMS value for that periodic function. Why do we care about RMS? It seems like it's just another thing to learn, but what you will learn in ECE 320 is the following. Let's say that we now have a resistor R, and we have a current that is through that resistor, and it's a cosine waveform. Let's say it has a magnitude of I sub m cosine omega t plus theta sub I. And let's say the voltage, passive sign convention, we're not really doing anything new in 320 that you haven't already become a little bit accustomed to here. But now do you notice that I'm changing the phases? One is subscripted as sub I, the phase of the current phasor. The other one is theta sub V, the subscript on the voltage phasor. And now in 320, you will learn those are the instantaneous current and voltages, but the average power of that resistor is just going to be the product of those instantaneouses changed up a little bit. We now have the average power of that resistor is now 1/2 Vm Im cosine of the angle between the voltage and the current, theta sub v minus theta sub I. That's the average power. So if you know the amplitude and the phase, a phasor of the voltage, if you know the voltage phasor and you know the current phasor, you can immediately write down, because cosine of theta v minus theta sub I is just a number. But this now allows us, do you see now what I'm going to do? I'm going to factor 2 into square root of 2 times the square root of 2, so that this is now V RMS I RMS cosine theta v minus theta sub I. And we don't have to worry about keeping track of that 1/2 coefficient. We just use everything in RMS units. In 320, you'll just be playing a lot with RMS units in Chapter 10, which is the power chapter. So we'll pick up with additional material in Chapter 9 tomorrow.